I'm going to talk about, okay, like in Unit 4, Inferential Statistical Concept, we already reached to, finished the t-test. So that is in the PowerPoint that is available on D12. So we already finished t-test, and I even solved one question for you about t-test. So you could see how we solve t-test type of question. Another method that we are going to talk about is about using p-value method. So what we are doing now in this part of the Unit 4 is all about testing the hypothesis. So we have two samples that they have different means, they have different standard deviation, and we want to see if the change in the mean or standard deviation of two populations is really because of some phenomena that we don't know, or is something that is due to the different in number of samples, different in, I don't know, like the type of samples that we have. So all this is to check that the difference in the mean of two populations or in the standard deviation of two populations is really due to some natural or inherent difference, or is only because we are choosing samples differently. We have different number of samples. That's why we have different type of means in two population. So you are familiar with this curve. Is a Z curve that you remember. Z curve, but like has positive values for Z. We have positive values for Z. We have negative values here. So what we do with this curve, for any Z value, we just go in this table and we can read the area on the right of that Z value. The same thing for the left Z, for the negative values of the Z. For each Z, we go to this table and we can go read the area on the the area on the left of the Z. The same thing here, the area on the left. Then we work on the T table. So in T table we had degree of freedom and confidence level or significance level alpha. This confidence level is 1 minus alpha, that we call it confidence level. Alpha itself is called significance level. So we are going to work with it a little bit later in this slide. So you remember that we had to calculate the t value, and then we had alpha. We were coming to this table and finding the t from this table. And if the t that we were calculating was, let's say, in this range, in the blue range, it was somewhere like here or here, then we were rejecting the null hypothesis. Okay, so this is one example that you already work on it. I think you have also some YouTube videos in your slide, you can watch them. Then yeah, like we had, that was for two-tail, that we were going to use the two-tail, this row here. For one-tail we have also a table like this. So we already used that. So in this video I'm going to use Z table, and we have also new table that we call it F table. So let's see what we have to do. Okay, I'm not going to go through the details of what I have, what is written here, because it might be a bit complicated for you. But I'm gonna just, I'm just gonna leave this slide for you. It's some additional information that you can just read them. So P value or P approach is something similar to t-test, the pooled t-test that we already used, with some small differences. And I prefer to use some examples for you. In that case, it's easier for you to understand this method. Otherwise, these explanations are kind of just for you to read them. But if you need some additional explanation, you can ask your question and I will be happy to answer. So it's just a method, is a critical value approach, like T approach, T test. We have also P value of P test. So we use the same equations that we have. So what we do here, we have to calculate again a parameter like T. So you remember, like we will see this, what are these parameters in one example that we have. So we consider our null hypothesis, we calculate T, and then we go like based on the level of the confidence that we go find our T, then compare this T with the T that we find from table, and if it's in the shaded area, we will reject the null hypothesis. If it's out of that shaded area, we will accept the null hypothesis. So for p value, we will follow the same method. So we have again two tail, left tail, right tail. All the explanations are here, but as I said, it might be a bit confusing for you, and I prefer to just show this in some examples, that what we have to do exactly for a p-value test, which is very similar to the pool t-test that I already solved one question for you. So okay, so what we do here for the first step, we have to, okay, we will write our null hypothesis and then alternative hypothesis. If is not, for a non-equal, we have two tail. For if the first mean is bigger than second mean, we have right tail, and if the first mean is smaller than the second mean, we have left tail. So what we do, we calculate T at the beginning, then we have the significance level alpha. We go find the T from for this alpha and the degree of freedom that we have. We go find the T value, and that is the T value that you will find from the table. Then you also calculate one T by using this equation that we have. So if that T that you calculate is somewhere here in the shaded area, so you will reject your null hypothesis. Okay, for the two tail. For the left tail, if your T is somewhere here, and for the right tail, if your T is somewhere here. In all those cases, you will reject your null hypothesis. Otherwise, you will accept it. So in the p-value, what we do, we don't go read the T table. We go read from Z table. Okay, this is for p-value test. We don't go to the T table. We don't go to T table. We go to the Z table. That's the only difference, the main difference between p-value test and t-test. Okay, so in t-test we go to the T table. In p-value test we go to the Z table. So now let's see what we have to do. I'm gonna start with some examples. So p-value here is nothing more than the kind of the Z value. Okay, so let's look at this example. Obtaining p-value for a pool t-test. So I'm gonna start with first example. In a left tail test, the test static value is T is this, and T is here -1. Assume degree of freedom 50. Calculate the p-value in each case. So here, p-value is nothing more than the area. It's very straightforward. P-value here is nothing more than this area here. Okay, so what we have to do, we have the degree of freedom. All right, so for part 1 I have degree of freedom 50, and for part A This is question 1, part A. I have t minus 1.872 and is also left tail. So left tail is here, somewhere here. So I have this is my figure, left tail. So this is my 0. This is the value that I have, minus 1.852. So since is left, I have to find this area here. This area here, it gives me my p value. So how we can find this area? We have this t here, okay? We have this t here, and we have to find the area. So let's go look in t table, okay? For degree of freedom 50, unfortunately we don't have, okay, we don't have the 50 here, so is a bit difficult to find it from here because we don't have I'm talking about this part 50 here, we don't have it, so we cannot easily find the area here, area on the left. And okay, so let me see, maybe I can find some other values here. Okay, just give me 1 second. Okay, t bigger than 50. Okay. So we cannot use the t table. We have to go through the z table. Okay, z table, my t is negative, so it's minus 1 point something. So I can go look at this table. So I need to find the area on the left, okay, on the left of my t. So my t is how much? I have it here. Minus 1.852 minus 1.852 minus 1.852. So in this case, help me to find it. So minus 1.8 is here, 0.5 is here, minus 8 is here. Just go all the way, and this is 0.5. So that will be my area. That will be this area here, the area on the left. So that is my z value, that is my p value, the area that I will find, which is 0.0322. So the answer here, p value is 0.0322. This is how we find it. So you can use this, you can use another value. I mean, you can use this t value and then again calculate the p value by using the table. And you can also do it with two tails. For two tails is also similar. So in two tails, what you have to do, I already solved one similar question. So two tail, for example, for part A, so this is your z, t is given, minus 1.66. Since it's a symmetric for two tail, so the other part will be positive 1.66. So what you can do, p value now is this area plus this area, all this area, these two areas together, that is my p value here. So for this question here, so all these two area, these two shaded area is my p-value. So what you can do, you can go to the z table for this t, for this z value, you can find the area on the left. Okay, since it's symmetric, that area is also equal to this area. So you just need to go to the z table and find this area, and this area multiplied by 2 gives you the p-value in this case. You can also do it for this example. But for now, yeah. So z table in general, this is the general method that we use to find p-value in this case. But we have another example that is more important. I'm going to talk a little about it. I'm going to talk about it a little bit now. But just let me to go back to t-table again. Okay. 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 So, but in general, for one point here, for high degree of freedom. Okay, don't forget that. If degree of freedom is large, the value, the z and t value, they are very similar. You see that the maximum z that we have is how much? Minus 3,4. For the positive is 3,4, something like that. This is the maximum z. So while in t-table, if you look at t-table, at very high degree of freedom, somewhere here, you can see that my t values are all almost, the maximum t that I have is 3.6, 3.7, something like that, okay, 3.5. But while if the degree of freedom decrease, we have much more bigger t. So that means this curve here becomes much narrow. It becomes something like that. At low degree of freedom, it becomes something like that. Very low. I mean, very narrow curve. So now this is not good. But yeah, this is for the very high degree of freedom. This is for very low degree of freedom. Anyways, I cannot plot it nicely here, so let me try maybe here. Yeah, here is easier because I have to write here on the photo. So this is for very a large degree of freedom. This is for very a small degree of freedom, so that it continues in the walls. Even this is not ideal. I will try to explain later. So that's all for this part now. Okay, just have a look at this example later, work on it a little bit, and then we will discuss more if you have any question. Now, yeah, I put also the z table here for you, in case if you need it. So now I'm gonna talk about, okay, if we have two samples, how we will use two samples with two different mean, two different standard deviation, how we will use the p-value approach. Okay, so the steps are quite similar to the poor t-test. We have to define our null hypothesis, then our alternative hypothesis. We have two mean and two samples, okay, N1 and 2 is like the two number of samples. We have also the SP, which is the standard deviation, is an equation, is a parameter that is S is for standard deviation, P is for pooled standard deviation. We call this parameter pooled standard deviation. That is the equation function of a standard deviation of two samples and the number of samples. So we calculate T. For T we need SP, that we will find it from here, and then we have to calculate the degree of freedom. Okay, now in this kind of example we go look at T table, not anymore the Z table. So degree of freedom here, for degree of freedom we calculate from this equation. So then we have to always know the significance level alpha. So after that we have alpha and we have our degree of freedom. We go to the T table and we find our T value. Okay, T value from T table, and if T, then we based on if my question is a two tail, left tail or right tail, we have to plot one of these figures. If it's right tail, two tail, left tail and two tail, we will plot it. This is the T that we will find it from the curve, from the T table. Then we compare, we have this df, and we have this T value that we calculate here. So we put it in this curve, and we go to we can find the P value by using this kind of graph. And after that we compare our P value with the alpha. Alpha is significance level that is given here. And how we do it? If P is smaller than alpha, equal to smaller than alpha, we will reject the null hypothesis. Otherwise we will keep the null hypothesis. This is how we do it. So I'm gonna solve one question for you, then it will be more clear for you. Yeah, so let's work on one example here. Example 9, water treatment facility. Okay, water treatment facility collect and record pH measurement data just before water is released into municipal water supply. In 2014, we have 24 measurements. That the average of pH of that 24 measurement is 6.154, and a standard deviation is 0.0023. The pH analyzer was replaced in 2017. And the measurement we have this year, we had 25 measurements, and the mean was 6.125. The standard deviation is 0.0012. At this 10% significance level, this is your alpha. Do the data provide sufficient evidence to conclude that this year pH has decreased? This year means the new year. Assume that the data are normally distribution. Okay, so this assumption is important because for all the curves that we have, Z table, whatever we have, whatever table, whatever curve we have, we assume that our data, they have a normal distribution, or the population has a normal distribution. The samples, they have a normal distribution. Otherwise, we cannot use this curve or tables without having this assumption. And population standard deviation is equal. So these two standard deviation that we have is for our samples, 24 and 25 samples here, 24 and 25. While this, we had a bigger, much more measurement than 24 and 25. That is those many measurements, let's say 1,000 measurements, that's my population. That is standard deviation of the two population in 2014 and 2015. They are the same. This is not very important. The most important assumption is this one, that the data are normally distributed. So then, okay, if you get p-value bigger than 0.1 is weak or no. If smaller than 0.01 is very strong. What is that? The evidence against null hypothesis. In this case is very weak. In this case the evidence are very strong. So now let's see what we have to do. Actually, I solved this example by myself and I scan it. I put it here for you. So what we have in 2014, we have 24 data. Mean is 6.154. The standard deviation is 0.023. In 2015, we have 25 samples. Mean 6.125 and S2 is 0.012 and significance level is also given 10% or 0.1. So then this is my example. So the null hypothesis here is the previous mean, which means this one, and the new mean, they are the same. Okay, this is, let's say, the engineer who is working in that plant is saying that the two mean in last year and this year, they are the same. That's a population mean. But the alternative hypothesis is no. The new year mean, which is this one, is less than the previous year. It has decreased. The new mean is less than the previous mean. It has decreased. So if you look at the previous slide, when the mean is decreasing, the new mean is smaller than previous mean, so it's a right tail. So we have a right tail here. So we have this kind of problem that that we have to go find the p-value and then compare this p-value with alpha, which is here 0.001. We compare our p-value with alpha here to see if it's smaller, bigger, and or no. So first of all, we have to calculate t. This is the t that we want, is this t here. This is the t that we want here. So the t is, we have an equation, x1 mean, first mean minus second mean divided by sp. Sp has a definition, divided by 1, square root of 1 over n1 plus 1 over n2. So before we start calculating this, we need sp. So sp is from this equation, n1 minus 1, s1 power 2, s1 is given here, n1 minus 1, n2 minus 1, s2 power 2, we have s2, divided by n1 plus n2 minus 2. We have all these values that we want. N1 is 24, n2 is 25. We have s1 and s2 from this table. We just plug them here, and this is what I have calculated already. So you can just double check my calculation. Once I have sp, I can go find my t. I put sp here, I have the rest, and I can find my t. So if you put all your x1, x2, sp, n1, n2, you can find t, which is 55.35. So this is your actually z value. Okay, this is your z value, which is how much? 55.35. So you have to go find the area on the right of this z. Okay, it's a very small area on the right of the z. Let's go to the z table to see if we can find that area or no. So let's go to the z table. This is a negative z. Our z is big, positive z. So you see that my z, the maximum z, positive z that we have is 3.4. 3.4 is somewhere here. Maximum z that I have is 3.4. Is somewhere here. That is your 3.4. Somewhere here. So that gives you the area on the right of z. It means here is almost nothing. This area here on the right of this z. This z is 3.4 or 3.5. Let me clean this. Yeah. So this area here for the z.4 on the right of z.4 is almost 0. This area on the right is almost 0. Why? Because the area on the left of 3.4 is 0.9997. Is all this. The whole area of this curve is 1. The area on the right of 3.4 is almost 1, is this much, 0.999 something. Okay, so it means this area on the right is almost 0. Is a very small amount, is maybe this much, 0.0003. Okay, 1 minus this value give you 0.003. So the area on the right of the z is very, very small. Okay, this is for z 3.4, while the z that I have is 55. So it can be like somewhere far here, and the area is almost 0, and is even less. Area on the right of this z is even less than this value. So that's why here in this part I have written the area on the right of this z is almost 0. Okay, this area here that gives me my p-value. This area, my z is 55. The area on the right of z based on the table is almost 0. So this area, which is my p-value, is almost 0. So now I have to compare my p-value with alpha. Alpha is 0.1. So my p-value is almost 0, which is much smaller than 0.01, and is even a small 0 is even smaller than 0.001. Okay, it's very small value, 0 is smaller than both alpha and this value. So is smaller than alpha, it means, let's go to this table. If p is smaller than alpha, we reject the null hypothesis and we accept the alternative hypothesis. Okay, we reject this hypothesis and we accept this hypothesis. It means we can say, with all this data that we have, the evidence that we have, we can say that the mean of pH measurement has decreased this year comparing with the previous year. Or we can, or based on this table, the p-value that we got is 0, which is smaller than 0.01. So we have very strong evidence against null hypothesis. Very strong evidence against null hypothesis. Against, it means rejection of null hypothesis. We reject null hypothesis because we have a very strong evidence, and we accept the alternative hypothesis. So this is one example, and I hope it was not that complicated. We have example number 10. Okay, so this two slides we just compare the pool t test with pool t-test with p-value approach. So the steps are the same. Totally we have 6 steps. The steps are the same. The first steps are the same. We have some assumptions. We define our null hypothesis. We define our alternative hypothesis. Then we have to know our significance level. We go find our t. We go find our SP. We calculate t. Then after that, if it's t-test, pole t-test, we go through this. We go through this approach. If it's a p-value approach, we go through this approach, this way. So in t-test, we already calculated. We calculated that t. This t will come from the table. This t here, they are coming from the table. You have also one t that you calculate from here, and then you have to see the t that you calculate is located where. Is located here, here, or here, here. Then you can decide to reject or accept your null hypothesis. For p-value, I already talked about it here. So now we have another example. Example 11. 2 tests of iron analysis were performed on a water sample. The mean for the lab measurement was 0.95. We had 5 samples, and for the analyzer was 1.1. We had 6 samples. S pooled, the SP is already given to you. You don't need to calculate it. Can we say at 95 confidence level that the means are the same? Here I'm saying the means are the same. This is your null hypothesis, but what we see, the lab measurements, the mean is smaller than the analyzer measurements. But here is saying no, it's the same. So we are going to use the p approach again here. We can do it with the pool t-test or p approach. So I will do it with p-value approach. You also do the pool t-test. Go through this method here. I'm going to use this method now, and you go do it through this method, and then we can compare our results with each other. So now I already solved it again, and I'm gonna just show it what I have done. So we have the lab measurement and analyzer measurement. For the lab measurement, I have 5 data. Mean is 0.95. For the analyzer, I have 6 data. The mean is 1.1. So the S pool is already given to you. S pool already given. So alpha, we have the confidence level. Confidence is 1 minus alpha, which is given to you 95% or 0.95, and alpha, which is the significance level. This is your significance level. Significance level is 0.05. So what we have here, we have null hypothesis that is telling us the measurements from the lab and the analyzer is the same. But what we see here, the measurement from analyzer is more than the measurement of the lab. The new mean is more than the lab means. So it's a left tail test. If you look at the table, it's a left tail test. So I have to calculate t here. This is, I have a notification here. So this is my t value here. Okay, so I have to go find my p value that I will find it from the table. I have to calculate t first. The t is here. We find it from this table, this equation. So we have x1, x2, s pulled, n1 and n2. I just plug everything in this equation. We have x1, x2, n1, n2. I just plug everything and I found my t, which is minus 3.64. So for this t, again, we have to go in the z table. For z minus 3.6, the area on the left. So if you look at, let's go to the z table. Let's go to the z table. This is my z table. My value, the value of the t, the value of the z that I have is minus 3.6. Okay, minus 3.6. So this minus 3.6, we want to know what's the area on the left of this z. You see the lower value that we have for the z table is minus 3.5, almost minus 3.4 plus 0.09. That gives you this much. So for the z, sorry, just let me clean this. So for the z, minus 3.49, the area on the left is this much. This is the area on the left, 0.0002. It's a very small area. So for minus 3.6, which is somewhere here, the area is even smaller than this one. It's almost 0. Okay, so I will keep this area, which is as a good estimation for the area on the left of z minus 3.6. So let's go back to our question. So now I have my, okay, I went to the table for the z minus 3.6 or 6.4, the area on the left. I found it a very small value, which is which is 0.0002. So now, okay, that area on the left, this area here on the left is my p-value that I found to be 0.0002, and I have to compare it with alpha. Alpha is the significance level, which is 0.05. So my p-value, which is this, is much smaller than the alpha. So in this case, I will reject the null hypothesis. It means the mean is not the same, and actually the mean has decreased. The mean has increased. So how do I know? I look at this method. So I calculated my p-value, which is smaller than alpha, so I have to reject the null hypothesis. I have to reject this and accept this. So the means are not the same. Actually the mean is increasing. So I also, okay, I forgot that I also did the pool test. So for pool test, what you need alpha, and you need the degree of freedom. Degree of freedom in this case n1 plus n2 minus 1. Just let me double check. Sorry, is minus 2. I did a mistake here. So you just correct it. So degree of freedom here is minus 2, not minus 1. So is 5 plus 6 minus 2, which is 11 minus 2, that give you 9. So this is how we calculate it. So then for t-test, we go to the t-table. For degree of freedom 9 and alpha 0.05, the area on the left, okay, because it's the left tail, and we have to go find the area on the we have to go find this area, this area here. So how we do it? For the alpha here, we have the alpha and we have the degree of freedom. We can go find the t on the right side. we can find this T, because that table that we have for the T gives us the area on the right. So we find that T, since this curve is a symmetric curve, so we just multiply that T by a negative sign and we find the T that we need to use for our calculation. So what I will do, I go to the T table and I find my T value for alpha 0.05 and degree of freedom 9. So let's go do that. T table. This is my T table. So I will use this T table for alpha 0.5, degree of freedom 9 here. So that gives me this T, okay, alpha, I have it, and I have degree of freedom, which T is this one, 1833. 1833. Okay, when I write on the photo, this table is a photo. When I write it here, which is on the PowerPoint, is okay, but when I write it on the photo, it becomes very slow. So the T that we find is this much. 1.833. So now I just go back to my example. So this is my T here. 1.8 instead of 2 now is 3. That, as I said, is I found this T here. Okay. Since the curve is symmetric, so you just multiply this T by a negative sign and you will get your T. So just multiply that by negative sign, so you will get T minus 1.833. So your T here is minus 1.833. So now this is the T from the table, and you have to also remark the T that you calculated by the equation. The T that we calculated by equation is here, minus 3.64, is located here. Okay, so this is the T from the table. This is your T, is located here, this one. So your T that you have calculated is in this area, in the shaded area. So for the left tail test, when your T is in the shaded area, you have to reject the null hypothesis. How we know it? Let's go back to this table. So for the T test, so you go calculate this T from the table that we did, and then if your T locates in this shaded area for the left tail, so you have to reject the null hypothesis. This is how we calculate it. So hopefully it was kind of, I know sometimes a bit complicated, but hopefully if you do some practice, it will be more, it will be easier for you to understand, so you can repeat watching this video many times, and at the end, if you still have questions, I will be available, so you can ask me and we can work together on it. So, okay, that was about this example. Okay, let me correct this part here too. So this is 833, the right value. And the reason is that I made a mistake here. I instead of having degree of freedom 9, I was using 10. But you see, the difference is not that much. It's only a very small difference that doesn't even change our answer. So the next topic that I'm going to talk about is F distribution. Okay, F distribution is also something related to, okay, So far we used t-test, pool t-test, or t-test or pool t-test, and also p-value approach to compare the mean of two samples. Okay, just give me 1 second, please. I just need to drink some water. I have been talking continuously for I think 1 hour now. Just let me drink some water. So now, okay. So far in t-test or the pool t-test, we compared the mean of two samples. Even in p approach, we were comparing the mean of two samples, and at the end we were making this conclusion that the mean is the same, or has increased, or has decreased. F distribution is also a similar process that we will use to compare the accuracy of two samples, the precision of two samples. And you know that accuracy of precision, it can be represented by a standard deviation. So in the F distribution, we compare the standard deviation of two samples. If the standard deviation has increased or decreased or is the same, that gives us some clue, some insight about the precision or accuracy of our measurement or our experiment. So standard deviation gives us some idea about the accuracy of or precision of our experiment, that we will test it by using F distribution. So it's the same procedure. We have null hypothesis, that alternative hypothesis. We have to calculate some parameter and then use the table, which is F table, and so on. So F distribution, you remember, like chi curve. In we use the chi curve to calculate the interval of variance or interval of standard deviation. So we use F distribution also here for testing our hypothesis about the precision, if the precision is the same, precision has increased or decreased. And in the for a standard deviation, we had the interval of a standard deviation, we had chi table. Now we have F table or F distribution, which is very similar to chi table. So F distribution or F table is a curve that has 2 degrees of freedom. It has 2 degrees. It's a curve that we have actually since we if you remember, we had different chi distribution depending to the degree of freedom. So here also we have many different F distribution depending to degree of freedom. And F distribution has 2 degrees of freedom. Okay, it has 2 degrees of freedom, that we call it the first degree of freedom, or numerator degree of freedom of numerator, and second degree of freedom or degree of freedom denominator. So first degree of freedom or degree of freedom numerator, second degree of freedom or degree of freedom of denominator. And we show it in this way: df, degree of freedom, 10 and 2. So 10 is the first degree of freedom or degree of freedom of numerator, and 2 is the second degree of freedom or degree of freedom of denominator. Okay, the properties of F distribution or F curve. We have many F curves, and each of them we show it with their corresponding degree of freedom. So for example, this is the F curve that has first degree of freedom 9, second degree of freedom 50. This is a curve that has first degree of freedom 10, second degree of freedom 2. So we have different different type of this table that you can see, different type of F distribution or F table. So the properties are again similar to chi table or chi curve. The area under the curve, under all the F curve or F distribution is 1. This area is always 1. The area under the curve is always 1. The curve start, all of the F curve, they start from 0 and they extend horizontally on the horizontal axis until infinity. Okay, until infinity. So as they go through they go to the right side, they approach to the horizontal line, horizontal axis they never touch it. They get very close, but they never touch it. And also the F curve is a right skewed. You can see that it will continue until infinite number on the right side. Is a right skewed curve. So that's some additional information. Okay, now what is table? F table. Okay, if we take each of the number on this curve and put it in the table, if we take each of the number from this table and we put it from this curve and we put it on the table, that gives us the F table. Okay, F table is all the numbers taken from these curves for the different degree of freedom. So F tables they are a bit specific because F tables they include both first degree of freedom, second degree of freedom, and another parameter which is alpha. Degree is a significance level. Okay, significance level. And so the F tables they contain four different information. First degree of freedom or numerator, second degree of freedom or degree of freedom of denominator. Alpha is the significance level and also the F value. So we have many F table. I'm going to show some of them to you in the next slide. But the most important thing is how to use them. So this is one table, one F table or F distribution. So you can see the first degree of freedom is on this row here. The second degree of freedom is here. This is first, this is second degree of freedom. Those values here inside the table, those are all your F values here. All of them are F value. And also this table is only for alpha significance level of 1%, 1% or 1% or alpha 0.001 on the right tail. Okay, so this is alpha is the area on this is the area on the right of the F. Okay, so we will see this later in some examples. We have the same table for alpha 5%, alpha 5%, or alpha 0.05. This is again, okay, now, okay, you know, we have different type of tables. I download them from different sources. So always pay attention to the explanation in the table. So in this table, column represents degree of freedom of numerator. Column is this one. Now this is the first degree of freedom. and the row here is the second degree of freedom. But while here this was the first, this was the second. So now is vice versa. The column is the first, the row is the second, and it's for alpha 5%. This is for alpha 2, alpha 2.5%, or alpha 0.020, 0.025. So again, this is first degree of freedom. This is second degree of freedom. By the way, I put the clean version of PowerPoint is already on D2R, so you can use this table as clean as on the PowerPoint without any of this annotations. And okay, now let's let's work on some example here. Okay, I'm gonna work on the first one and I leave the other one to you. So from a F curve, for degree of freedom, first is 4, second is 12. Find the F value, the value inside the table, for a specified area to the right. It means alpha. This is alpha. Alpha 0.05 or 5%. So I have to go to which table? This is the table for 5%. First degree of freedom is 4. Second degree of freedom is 12. So my alpha is, my F value is located here. First degree of freedom 4. Second degree of freedom 12 is 5, 9, 12. 5, 9, 12. So the F value here for this part is 5.912. Okay, so you can do it for the two other alphas. For this alpha and this alpha, you have to use the other tables. So now, okay, what is the F test? We have F table that we use F test to find the F. We use the F table to do the F test. As I said, F table or F distribution is used to do T to F test for comparing the precision or accuracy of one old and one new old and new phenomena, old and new experiment, old or new analyzer. Okay, so we compare the precision. Precision is represented by a standard deviation. So for the all tests that we had, pool T test, P approach, P value, they were all comparing the means. Now we are going to use TF test to compare the standard deviation. That is also a measure of precision or accuracy. Let's say we replace old analyzer with a new one, and we see that there is a difference in the standard deviation. So like it means that there is a difference in the standard deviation, means that there is a difference in the precision of our measurement. So can I say that the precision has increased or decreased, or is the same or is different? So to do those kind of conclusion, I have to do a F test. So now let's do the F test. F test, okay, what we do in F test is is in this way. Is always, okay, we have two samples with two standard deviation that is given to you. So we have some assumptions, the samples are normally distributed, independent sample and so on, that we have always this assumption. So now we want to compare the standard deviation of these two samples. Null hypothesis again is that the standard deviation of the two samples are the same. Null is the standard deviation is the same. Alternative hypothesis can be again two-tailed. No, they are not the same, they are not equal. Left-tailed, first one is smaller than second one. Right-tailed, the first one is bigger than second one. So we define our null and alternative hypothesis based on the question that we have. Then we have to know what is our significance level, or alpha, which is the area on the right of F value. We calculate our F value, the first standard deviation power 2 divided by second standard deviation power 2. You know that a standard deviation power 2 is also called variance. That is usually the larger variance divided by the smaller variance. Most of the time is like that. So we calculate this F, and then, so we have alpha, we have number of samples, degree of freedom. We go to the F table and we find the F from F table, and we have one F that calculated here. So then we compare them together. How we compare them? We use this approach. So for now, forget about this approach. This is not something that we are going to talk about it. This approach is more important. So based on, I have my null hypothesis, alternative hypothesis, I have my alpha, I have also my F. Then I come here. What I do here, I go find my, okay, based on if it's two-tailed, left-tailed, or right-tailed, I go find one of the F, I go find the F from the table. I have alpha, I go find the F from the table, which is alpha is alpha is the area on the right. So how do you find it for the table, F table? I need alpha, that I have it. I need degree of freedom, first degree of freedom and second degree of freedom. So first degree of freedom is n1 minus 1, second degree of freedom is n2 minus 1. Then based on if it's right tail, left tail, or two tail, I have the F value that I have calculated, and I have the F value from the table. So if my F locates in the rejection zone, like in the shaded area, so I will reject the null hypothesis. If not, I will accept. This is the whole process. Now I'm going to solve one question for you. So how again, I will repeat how we use this curve. This is the F that we find from the table. For the table, we have alpha and we have degree of freedom. We can go find the F from the table. So the F that we find from the table can locate anywhere in this curve. If the F that, the F from the table is here, the F that we calculated here, this F can be located anywhere here in this horizontal axis. If locates here, this is non-rejection zone. We don't reject the null hypothesis. If my F is here, we will reject the null hypothesis. So now let's look at this example together. Result for the lab analysis and a process analyzer are compared for precision. The confidence level is 90%. So confidence is, this is 1 minus alpha, alpha is 5. So we have two groups of data. First group 10 data, the mean is 2163, the standard deviation 0.036. And the second group we have 13 data, the mean and standard deviation. Question: can we conclude that at a 95% confidence level, that precision is in group B has decreased? Precision in group B has decreased. So you see that a standard deviation in group B is less than a standard deviation at group A. A standard deviation is a measure of precision of our data or measurement. Okay, so can we say only by this data that we have, can we say that the precision has decreased or not? Okay, because the standard deviation has decreased, can we say with 95% confidence level that precision decreased or not? So to do that, we use t-test. We apply t-test to do so. So I'm gonna solve this for you now, and let's see what we have to do. So group A, this is my N1. Group B, this is my N2. This is my S1. This is my S2. Confidence level is given 1 minus alpha, 95%, or 0.95. Alpha is 0.05. So my null hypothesis, let me start from here. My null hypothesis is that the standard deviation for the two groups is the same. Alternative hypothesis is that the standard deviation, oh no, this is not good. Okay. Alternative hypothesis, the standard deviation for group 2 is less than group 1. Group 2 is less than group 1. So sigma 2 is smaller than sigma 1 is which type? Left tail, right tail, or two tail? Let's go look at this table. Sigma 2 is smaller than 1 is right tail. This one here. Okay, right tail. So right tail means I have to look at this curve here, right tail. So what I have to do, this is the test that I have to work on it. So I have alpha, I have to go find the f value from the table, and I have to also calculate a f from the equation that I have. This equation, s1 power 2 over s2 power 2. S1 power 2 over S2 power 2. S1 is 0.036 power 2. S2 is 0.029 power 2. That that I already calculate this value. That gives us 36. Yeah, this gives us f 1.54. This is one f that we need. We need to go find another f from the table. Okay, we need to find another f from the table. What is that f? For alpha 0.05, degree of freedom. Degree of freedom n1 minus 1, n2 minus 1. How we know degree of freedom is like that is based on the definition. Degree of freedom n1 minus 1, n2 minus 1. So n1 is 10. This is my n1, this is my n2. n1 is 10, so n1 minus 1 is 9. I don't know what's wrong with this table now. Is 9. n2 is 13. n2 minus 1 will be 12. So for 9 and 12. So I have to go to this table, alpha 0.05 or 5%, and degree of freedom, first degree of freedom 9, second degree of freedom, first degree of freedom 9, and second degree of freedom is 12. So let's go to the table. This table here 5%. So let me just clean the table a little bit. So this is my 5% table. First alpha is, okay, column represent first degree of freedom. This is the first degree of freedom. And row is the second degree of freedom. First degree of freedom is 9. Second degree of freedom is 12. So 9 all the way until 12. So this is your F alpha, F value, 3.073. So the F alpha that you find here is 3.373. So your alpha that you find from table is here, 0.073. The alpha that you have, let me change the color here. Maybe you are fed up of the red light, the red color, so I'm gonna make it blue. So the alpha that you have calculated here from the equation is here, is somewhere here, 1.54. So this is 3. The alpha from table is 3.073. The one that you have calculated is here. So your F is located in this region. So this is my rejection region. This is accept. This is rejection. This is acceptance region. Why? Let's go back here. So if this area is rejection, this area is acceptance. So the F that we have calculated is here in the acceptance area. So that means we accept null hypothesis. We accept that precision is the same as before. For the two groups is the same. Or we reject the alternative. We reject the alternative hypothesis. We reject that the precision in the second group is less than first group, or the precision has decreased. We don't accept this, we reject this. We accept the null hypothesis and we reject this one. So can we conclude that in this confidence level, precision in group B has decreased? No, we cannot conclude the alternative hypothesis. That's how we do this test, this kind of exam. So, and the last example is quite similar. I also solved it for you, and let's look at this together. So we have a water treatment facility X that collect and measure the pH that do some pH measurement. In 2014 it did 24 measurement. The mean was this, the standard deviation was this. And in 2015 we did 25 measurement and mean was this, the standard deviation was this. At this significance level, alpha here is 0.1%. At this significance level, Do the data provide sufficient evidence to conclude that the precision in 2014 is greater than 2015? Precision in 2014 is greater than in 2015. So use the critical value and p-value. I'm not going to talk about p-value because we already talked about it. This is more important, even in terms of exam, in terms of exam or test. Using critical value test, t-test or f-test, like the example that I already saw, is more important. This p-value approach, I'm not going to answer about. So let's see what we have. So we have in 2014, we have 2015. In 2014, number of samples 24. In 2015, number of samples 25. The mean in 2014 6.154. In 2015 6.125. In the standard deviation in 2014 0.0023. In 2015 0.0012. All right, and significance level is given 0.1. So now null hypothesis, the mean, the standard deviation or precision is the same. Alternative hypothesis is that precision in 2014 is bigger than 2015. This one here that you see, 2014 bigger than 2015. So is it a left test, a left tail, two-tail, or right tail? Left tail, two-tail, or right tail? Let's look at the table. Sigma 1 bigger than sigma 2. This is my table. Sigma 1 bigger than sigma 2 is right tail. Again, is I have to use this curve. Okay, this curve. Be careful that this F table or F curve is not symmetric anymore. Okay, it's right skewed. So I have to use this like previous example. So I have to go find this F from the table. I have to find this F from the table and compare with the F that I calculate. I have to calculate my F as well, which is S1 power 2 over S2 power 2. S1 power 2 is 0.23 power 2, 0.12 power 2. So 0.0023 power 2, 0.0012 power 2. If you calculate this, I already calculated, you will get F 3.67. We have another F that we have to go look at the F table. For alpha 0.1, degree of freedom, we have 2 degrees of freedom, N1 minus 1 and N2 oh, I don't know why it's like that, N1 minus 1, N2 minus 1. So my degree of freedom N1 is here. 24 minus 1, that gives you 23. And 2 is 25 minus 1, that gives you 24. So the F table for this alpha I have given to you in the next slide is here for alpha 0.01%. So degree of freedom, first is 23, second is 24. First is in the column, second is in the row. 23 and 24. So 23 all the way up to here. That is your F5. 3.822. So the F that you calculate is 3.822. Okay. So where is your F? Your F is somewhere here. 3.67. So this is the rejection of null hypothesis. This is this area here, all this is the acceptance of null hypothesis. So your F is in this region. So you will accept null hypothesis. So it means the precision is the same in these 2 years. The precision is the same, or you will reject the alternative hypothesis. You accept this, you reject the alternative hypothesis. Rejection alternative hypothesis means no, we don't have enough evidence to say that the precision in previous year in 2014 is the precision in 2014 is more than the precision in 2015. We cannot say that. We don't have enough evidence. So that's all about Unit 4. So this is a long video. You don't have to watch it all together in one shot. So you can watch it, like different parts, different examples, depending to your time. And I hope you will enjoy it. As